I wanted to show you the graphing of some real data that indicates the use of exponential and logistical functions. And this is real data from the coronavirus cases based on the early days. And so these numbers, X1 is the day from when they started collecting, and Y1 is the number of cases. This was initially in China, and it was collected for the first 34 or so days. And I actually began with a slightly shorter data table going from day 1 up to day 21, and I wanted to show you the graph of that. So when we hit that, it shows all of those points graphed, and you can see it makes a very nice looking graph that looks like an exponential graph. Now if we wanted to create an equation based on that, Desmos has a very nice function which is called regression, and I'm going to use the second data table, which is the shorter data table, to see what kind of equation I would get if I try to make a line. So the linear format is going to be, so I'm going to use y2 because those are the y values in the second table, is equal to ax plus, and I should use ax2 as the input, and again for regression I'm going to use this squiggly. So y2 is with regression ax2 plus b. And we can see there's a line there, and that's a respectable looking line, and it's got an r squared value of 0.94, so that's pretty good correlation. The black dots do differ from the line somewhat, but they are relatively close. Now if I thought, this looks more like an exponential graph, what I could do then is type an equation that has the shape or form of an exponential. So I've got here y2, and again use the squiggly for regression, but I'm going to say a, and this time let's make it times e raised to the, and there's going to be potentially a constant, so I'm going to make it b and then x2. And let's turn on that graph and see how it looks, and that is substantially closer. Those points follow that line very, very nearly. And if we look at the r squared value, it is 0.987, and so that is better. Now when we look at these parameters a and b, these are the constants. So when you had this linear equation, the slope was 60 and the b was a negative 198, and that was because here when we initially began, the slope of the line tends to push it lower than 0. But this a equals 60 means that we are, if we're going along in this linear way, we are adding 60 new cases per day. However, the exponential graph does describe it more precisely. So now what I'd like to do is to go up to this data table and show you those green points, and that's what happens after day 21. Is thankfully that the virus, the number of cases, was starting to level off. It wasn't decreasing, but at least it wasn't rising so rapidly. And so this description, if I were to type in here y1, which is the complete data table, and x1, you would see this exponential graph. It's still pretty good, but the r squared value has decreased a little bit. And this leveling off, again, tends to indicate that perhaps the exponential graph is not the best model. So now I'm going to demonstrate what happens if we use another model, such as the logistical model. So here I've typed in the equation for the logistical model, and I'm going to take away the graphing of the lines so that we can see this more clearly. But when we graph according to the logistical model, that blue curve very, very closely follows not only the initial early data, but even the later data. And so we can, again, create a function which follows this data very closely. The r squared, the correlation, is 0.9991, which is really amazing considering this is real life data.